Hello everybody, welcome to this lecture on tree address codes. So we saw in the previous video that intermediate code makes the process of conversion from source language to target language a bit easier, and also it helps in the optimization process of the code. So the two previously discussed intermediate codes were syntax tree and postfix notation. So today we're going to look at the very commonly used intermediate code representation, that is the tree address code representation. So tree address code is represented in the form something like this. A is assigned B of C. So here B is the first operand, C is the second operand, and A is the result. And of course, this is the first, this is second, this is the result, and this is the operator. Okay, so it is all code is represented in the form of a sequence of statements of this format. Okay, and this A, B, C, all these can either be programmer defined variable names or compiler generated temporary names. So tree addresses, because it contains, it's called tree address because there are three addresses for B, for C, and for A. And for the operator, it is usually represented by some opcode. So for example, if I have a expression like this, y into z, okay, so if I want to express it in tree address statement, then I will write something like this. Say t1 is y into z. So t1 here is a temporary compiler generated address. Y and z are variables defined by the user. And then t2 is what? X plus t1. So both of these statements, they have three addresses. Okay, they are of this format. Okay, so these are tree address statements, tree address codes. Now there are many common types of tree address statements. Common tree address statements are there. So you have the assignment statements. So assignment statements are there. So when you have something like this, A is assigned B op C operator. Op is a binary operator. Or you may have something like this, where op is a unary operator, or I may have single assignment like this. So here I have, this follows the exact format of tree address. Here I have the first, the second operand is missing. So for that, it will not, the address of the third will be empty. Here address, the two things are missing, that is the operator and the other operand. So those will be empty. Okay, so this is a assignment operator which you can represent using tree address. Then you have unconditional jumps. Unconditional jump statements. Unconditional jump is represented using go to. So say go to L. So this means go to the statement L at tree address statement. Go to the statement with the label L. Or you can also have conditional jump. So I can have something like this. If a relational operator, rel op is the relational operator B, go to L. So this is a conditional jump. So if this evaluates to true, then jump to the L at tree address instruction. Then you have subroutine calls. Subroutine calls, by subroutine calls means I mean function calls. So it can be something like this. Say P is the name of the function, and A1, A2, all these up to an, these are the parameters. Okay, so this in the form of a tree address statement would be like this: param, this indicates that a1 is a parameter, param a2, all the parameters an, then call p and all the previous n parameters. So this is the tree address statement for procedure call. Then you can have array indexing, that is indexed assignment. So I may have something like this: A is bi, okay, or I may have ai assigned b. Okay, so these are all tree address instructions. Then I can have pointer operation, like say A is holding the address of B. This is a pointer assignment. A is a pointer, B or A is star B, okay, or star A is B. So all these are pointer assignment statements, and we can have these can be represented using your tree address codes. Now comes the implementation part of it. So implementation. Implementation of your tree address codes. So there are three ways in which it can be implemented. The first one is called quadruples. Then you have triples. And then the third is called indirect triples. So in a quadruple, it consists of a 4-field structure. So what are the structures? This is the structure of a quadruple. It has got 4 fields. The first one is for the operator. The second is for the first operand. Then the third is for the second operand, and this is for the last one is for the result. Okay, so we may have different opcodes for different operators. Like say if it is integer addition, we may have different opcode for integer addition. Floating point addition, we can have different opcode for that. So let's look at this example. So here I see this is the statement: A is assigned minus B into C plus D. So let us write it in tree address code. So first of all, say T1 is assigned minus B. So we saw for assignment of statement, we can write it like this. Then next T2 is C plus D, and T3 is T1 into T2, and the last one A is assigned T3. So this is your tree address set of instructions, tree address instructions for executing this in this particular statement. So as quadruples, they are represented in maybe say, let's say in a table kind of structure. I can think of it something like this. So first is op, then arg1, arg2, and result. Okay, so one more entry here to indicate which is the operation. So this is first operation is 0, so this is the one. So here operator is unary minus, let me write u minus. First argument is B, okay, there is no second argument, and the result is in T1. For the second one, this is 1, that is this statement, okay, operator is binary plus, then first argument is C, second argument is D, and the result is stored in T2. For the third one, 3, operator is multiply, first operand is T1, second operand is T2, and result is stored in T3. And for the last one, this is 2, this is 3. We are starting from 0, so 0, 1, 2, and 3. So here I have operator is assignment operator. First operand is T3, there is no second operand, and result is stored in A. So these are the quadruples, and here A, T3, T2, T1, all these can be represented as your symbol table, pointers to symbol table, pointers to the symbol table. Okay, so this is your quadruple. The next form of tree address code is implemented in the form of triples. So triple means again tree fields structure. So op, argument 1, argument 2. So the result field is not there anymore. So the result field would be, if it is a temporary variable, it would be represented by the statement that is computing the temporary value. So you don't use a separate temporary value. So let us see for the same example. This is our triple. So this indicates the op, then arg1, and this is arg2. So our first statement was this, T1 assigned minus B. So we are not going to use T1 anymore. So this is statement 0. So U minus, that is, let me write it as U minus, unary minus, argument is B, and the result is stored in this statement itself. Next I have T2 is assigned C plus D. So I'm not going to use T2 anymore. Operator is plus. First argument is C, second argument is D. Okay. Then for the next one, that is statement number 2. Okay. This was multiply T1, T2 and store it in T3. So all are temporary. So now instead of, since we have not used T1 and T2, so we are going to refer to it by the triple itself. So where it is computed. So here T1 was computed in statement number 0. T2 was computed in statement number 1. So we will write operator is multiply. So statement 0, first argument, statement 1 would be the second argument. Okay. And so statement number 2 now will hold our minus B into C plus D. And the last statement was assignment of A. So assignment operator A, and what was assigned? The result of this computation. So we will put 2 out here. So this is your triple. This is how we use this triple. So it helps in saving some kind of space. And we don't need all those, the entries in the symbol table is greatly reduced by this. The last implementation is in a form known as indirect triple. So in indirect triple, we have, this is the triple that we had. So in indirect triple, we have a format like this, where we have, instead of referring to the triple, we have pointers to the triple entries. So if this pointer to first, say, let me call it, let me start the count from 100. So this is 100, this is 101. So this is pointing to this triple, this is pointing to this triple. So 102 would be 2 here, 103 here would be 3 here. So each of these is pointing to the triple. So this is known as your indirect triple. So these were the 3 kinds of implementation of tree address codes, that is using quadruples, triples and indirect triples. Now the question that arises is that how do we compare the 3 methods? Which one is better? Which one is not so good? Where are these useful? Okay, so The first, in quadruples, the temporary variables are stored in the symbol table, as we have seen. But in the triples, they are not. Triples and indirect triples, these temporary variables are not stored. So as a result, the assignment of the memory locations in triples is deferred till the code generation takes place. Okay, so if any optimization has to be performed, in that case, you will not do the memory location assignment at the intermediate code generation. You can defer it till the actual target code is generated. So you can do a lot of optimizations. Also in quadruples, sometimes when we want to do some optimization, sometimes we might want to interchange instructions. So certain optimization requires that instructions are interchanged. That means instead of doing 2 first, we will do 3 first. Let's say for example, so I have 4 instructions, 1, 2, 3, 4. This is the order in which I have generated my intermediate code. But I find that by in order to optimize, I should do 3 first, then 2, then 0, then 1. So I might need to reorder the instructions in the tree address code. So in quadruples, it becomes easy because they are not linked to anything else. Like you can see in quadruples, we are not doing any. We can easily do this interchanging of instructions. It will not affect the others. Okay, but in case of triples and indirect triples, we are referring to the previous statement. Okay, like here we are referring to the statement number. Okay, so when we do interchanging, then this may create some problems. And in indirect triple, such problems will not occur because you are not referring to the you are simply having a pointer to the triple. So if you have changed the order of, say, this to from 0, 1, 2, 3 to, say, 2, 3, 0 and 1, okay, then all you have to do is change here because these are pointers. So you just change this. The first one would be 2, so you change the pointer to 2, then you change to 3, then this you change to 0, and this you change to 1. So your comparison, that is the that in indirect triple, this changing of the ordering of the instructions will not make much of a difference. So because why we're talking about this, because in optimizations we might need to do these interchanges. So that was about your tree implementations now of tree address code. Now in the next video we can look into different types of expressions and constructs, programming constructs like Boolean expression, arithmetic expressions, and so on. And then we will see their tree address code generation.